So we're going to explore here sort of how another way we can find empirical formulae for compounds, for unknown compounds, from in this case from reaction data. So basically in this area, the idea of conservation of mass is very important. Okay, this area kind of uses a few ideas about stoichiometry and about conservation of mass to really allow us to calculate the empirical formula of a substance given the data associated with its reaction. So the conservation of mass is very important. And this allows us to get to the molar ratio, which is what we know we need to find the empirical formula of a compound. Okay, so this is the key point we need for an empirical formula. So basically, conservation of mass means that, in a given reaction, we've got, some reactants here, some products here. The conservation of mass merely states that, if we have a certain number of atoms of a specific element on this side, then we have to have the same number of atoms of that specific element on this side. Okay, and we're going to use that. We use that idea in this process to find empirical formulae of reactants from the data of products. So if we have some data about products here, we can use this data to figure out more data on reactants, just like in any stoichiometric sort of context. Any stoichiometry allows us to use, to translate between, the number of mole of reactants to the number of mole of products and vice versa. However, in this case, rather than finding the number of mole, we're finding the molar ratio, rather than finding the number of mole of a specific, substance, we're using the number of mole of specific atoms to allow us to calculate the empirical formula. So this is all about number of mole of atoms. So this is what it's all about. So basically we're going to using the data that we have on the products of a reaction, we're going to figure out the number of mole that we have of different elements in the product. And then we're going to use that data on the number of mole we have of the different elements to figure out the number of mole we start with in the reactants, and thus from there the empirical formula. So let's have a bit of a look at an example. So let's say we're given a compound A, and A contains oxygen, carbon, and hydrogen, and we want to find the empirical formula of compound A. Now we're told that compound A, we're told that 7.95 grams of compound A it combusts. So the combustion reaction is basically the reaction of compound A with oxygen. That's what happens when something combusts. Not with, but this combusts to produce so we're producing 9.54 grams of water and 17.34 grams of carbon dioxide. So we've gotten this sample of compound A. We're just told that it contains oxygen, carbon, and hydrogen. We've figured out that it weighs 7.95 grams. We've combusted it, and we've produced 9.54 grams of water and 17.34 grams of carbon dioxide. Now we want to figure out the empirical formula of A. So we know that in a combustion reaction, we've got this compound A reacting with oxygen to produce hydrogen and carbon dioxide. Now if we look here, we've got this data about the products here, and we know that all the hydrogen in this water must have come from reactant A because there's no hydrogen over here. Similarly, all the carbon in the carbon dioxide here must have also come from reactant A. So that's going to be our first step, is to figure out the mole of hydrogen and the mole of carbon that we end up with in our products here. So we know we've got 9.54 grams of water. So we want to find the mole of water. So we're finding the mole of water. That's going to be equal to the mass divided by the molar mass. So 9.54 divided by 18. So that gives us, we've got 0.53 mole of water. And from there we can find the mole of hydrogen, which is going to be double this, because for every water molecule we've got 2 hydrogen atoms. So we've got 0.53 mole of hydrogen. Then we're going to have 1.06 mole. Sorry, for 0.53 mole of water, we're going to have 1.06 mole of hydrogen. Now if we look at the carbon dioxide, then if we find out the mole of carbon dioxide, it's equal to 17.34 over the mole. So the mass divided by the molar mass. So the molar mass is 44.0. That's 12 from carbon and 2 lots of 16 from the oxygen. So that gives us 0.40 mole. Now, from there we want to figure out the mole of carbon, because that's the element that we're looking at. We're looking at the conservation of carbon to figure out the amount of carbon over here. So we've got 1 carbon in every carbon dioxide molecule, so the mole of carbon is also going to be 0.40 mole. Now we need to figure out the number of mole of oxygen that were in this 7.95 gram sample of compound A. Now we can't do this by conservation of mole because we've added some unknown amount of oxygen here. This equation here is not balanced, so we don't know the amount of oxygen that's reacting for every sort of mole of A. So we can't use conservation of mass to figure out the amount of oxygen in here. So what we're going to do, we know we've got 7.95 grams of A. So we know that A consists of hydrogen, of 1.06 mole of hydrogen, 0.40 mole of carbon, and some oxygen. So we know that we can work out the mass, the amount of oxygen in compound A, using these two values, using these numbers over here. So the mass of hydrogen, we know the molar mass of hydrogen is 1.0 grams. So the mass of hydrogen is 1.06 grams. Now we know that the molar mass of carbon dioxide is 44.0. So mass of carbon is going to equal 0.40 times 44. And that gives us we've got a slight mistake here. We've got 0.40 mole of carbon, and we know that the molar mass of carbon is 12, not 44. So we've got 0.4 times 12 is equal to 4.8 grams of carbon. So we know that in this 7.95 grams of A, we've got 1.06 grams of hydrogen, 4.8 grams of carbon. So the number of grams of oxygen is going to equal 7.95 minus 4.8 minus 1.06. And that's going to give us 2.09 grams of oxygen. So from there we can figure out the number of mole of oxygen, and then we can work out a molar ratio between carbon, hydrogen, and oxygen. So the mole of oxygen is going to equal 2.09 over 16. That's going to equal 0.13. Mole. So we figured out all these values for mole. So now we've got to figure out the molar ratio. Now, so we'll make some room here. So we know that we know the number of mole of each. And to figure out to convert this ratio at the moment, we could say that carbon to hydrogen to oxygen is equal to 0.4 to 1.06 to 0.13. We want to convert this to a whole number ratio so we can get to an empirical formula. To do that, we divide all of these by the smallest number, which is 0.13. So 0.4 over 0.13 is equal to 3, and 1.06 over 0.13. Remember, we're using the full values, not just the rounded values here. So that's approximately equal to 8. So that means that this ratio can in fact be rewritten as 3 to 8 to 1. That gives us, if we have carbon to hydrogen to oxygen in that ratio, that means our empirical formula is C3H8 0, which is propanol. So that is our final answer. So what we've done here is we already knew the what elements were in compound A, and we knew its initial mass, and we used conservation of mass of hydrogen, the conservation of hydrogen and the conservation of carbon to figure out the number of mole of hydrogen and the number of mole of carbon in this 7.95 gram sample. From there, we couldn't use conservation of mass of oxygen because oxygen was being added. Not all the oxygen in the products had come from compound A, whereas all the hydrogen, all the carbon in the products had come from compound A. So we couldn't use, more oxygen had been added, so we couldn't just analyze the amount of oxygen on the right-hand side of this equation. So to do that, we subtracted the masses of hydrogen and of carbon in sample A from the mass of sample A to work out the mass of oxygen in sample A. We've got the mass of oxygen there, and from there we can figure out the mole of oxygen. And at that stage we knew the value of the mole of hydrogen in compound A, the mole of carbon in compound A, and the mole of oxygen in compound A. So from there we had the molar ratio that we're always striving for when we're finding the empirical formula of a substance. And so from there we can figure out the molar ratio in sort of with whole numbers here. And once we have this whole number molar ratio, we could then translate that to the empirical formula right here. So that's kind of how we go about finding empirical formula from a reaction. We analyze the conservation of mass rather than just looking at the number of mole of carbon dioxide and the number of mole of water. Here we looked at the number of mole of carbon in particular and the number of mole of hydrogen in particular. So we analyzed the amounts of the different atoms, the different elements on the product side to figure out a similar amount on the reactant side, rather than looking at the entire chemicals or the entire chemical formulae in there sort of as a whole. So that is how we find the empirical formula of a substance, of an unknown substance, from reaction data.